Did we just witness an apparition? Not the ghost of a departed soul, but something far more profound, the spectral echo of the universe itself. A phantom born in the very first fleeting instant after the Big Bang. Something considered impossible has just registered on our instruments, something that, by all accounts, was never meant to exist. And if the theoretical physicists are correct in their interpretation, it didn't originate from just anywhere in the cosmos. It emanated from a black hole, but not the kind we're used to hearing about, a voracious giant tearing apart a star. No, this was something entirely different, a black hole in its final death throes, detonating, broadcasting its ultimate secret across the vast expanse of space. Picture a bomb in your mind. Now, imagine that bomb has been silently counting down since the dawn of time itself. For 13.8 billion years, it has remained mute, invisible, adrift in the cosmic darkness, simply waiting. In essence, it was a trap constructed purely from gravity. But today, that timer reached zero, and the subsequent blast was so brilliant, so saturated with energy, that it shattered every single model of physics we currently possess. We have just observed a black hole explode, and within the residual debris of that cataclysmic event, we may have unearthed the solution to, well, nearly everything. The enigma of dark matter, the mysteries of the Big Bang, the grand unification of quantum mechanics with general relativity. It's all potentially there, hidden in the aftermath. Hello and welcome back. If you've been a regular follower of this channel, you'll know we've been intensely focused on the puzzle surrounding Comet 3I Atlas. We've been scouring for anomalies, searching for any telltale signs, but as the entire world was fixated on that single comet, something else entirely erupted from the depths of the void, something far stranger. It turns out that Atlas might merely represent the visible tip of a much larger iceberg, in a universe far more turbulent and dynamic than we ever imagined. Today, we stand on the precipice of a new reality. We're going to explore one of the most monumental discoveries in the entire history of astrophysics, a revelation that fundamentally challenges our understanding of the darkness. We're going to discuss the recent detection of a seemingly impossible particle and the groundbreaking theory suggesting we have, at long last, witnessed a primordial black hole reach the end of its existence. If you're passionate about deep explorations into the unknown, whether it's enigmatic comets or stellar detonations, be sure to hit that subscribe button and give this video a like. Your support helps us bring these massive, mind-expanding stories to you. Now let's rewind the clock back to the precise moment of impact. To truly grasp why this discovery is so profoundly shocking, we need to begin with the conventional narrative surrounding black holes. The story you were taught in school, the story that insists black holes are cosmic one-way streets. They are the universe's ultimate no-exit motel. You can check yourself in, but you are never, ever checking out. According to classical general relativity, Albert Einstein's magnum opus, a black hole is a remarkably simple entity. It's a region of spacetime where gravity has become so overwhelmingly powerful that absolutely nothing, not a single thing, not even light itself, can break free. The moment you cross the event horizon, you are effectively erased from the observable universe. You are gone. And the black hole itself, it simply persists. It expands. It consumes. It grows more massive, but it never truly dies. In the pristine mathematics of Einstein's theory, a black hole is an eternal object. It's an indelible scar on the face of reality that never heals. However, everything changed in the 1970s when Stephen Hawking decided to rewrite the rules. By applying the principles of quantum mechanics to the extreme environment at a black hole's edge, he stumbled upon something bizarre. He realized that the vacuum of space is not a true void. It's a seething, turbulent foam of virtual particles, constantly popping into existence in matter-antimatter pairs, only to annihilate each other an instant later. But right at the boundary of a black hole's event horizon, something dramatic unfolds. One member of this particle-antiparticle pair gets swallowed by the black hole, while the other manages to escape. That escaping particle is no longer virtual. It becomes real radiation, stealing a minuscule, almost negligible amount of energy from the black hole to pay for its existence. This became known as Hawking radiation, and its implications for the black hole were terrifying. If it's losing energy, it must be losing mass. It is shrinking. It is evaporating. But this process is agonizingly slow. For a black hole with the mass of our Sun, the evaporation time would be astronomically longer than the current age of the universe, trillions upon trillions of years. So, for all intents and purposes, we were convinced we would never, ever witness a black hole's demise. It was a theoretical event relegated to a future so distant it would never be observed by humanity. But the universe has a rather cruel sense of humor when it comes to our practical assumptions. Because physics also tells us that the smaller a black hole is, the hotter it becomes, and the faster it radiates its energy away. A supermassive black hole is practically ice cold, but a minuscule black hole, a microscopic one, blazes like a furious stellar furnace. And right at the very end of its life, when it has shrunk down to the size of a single proton, it shouldn't simply fade quietly into nothingness. It should flash. It should release all its remaining pent-up energy in a single catastrophic split-second burst, a final, violent exhalation, an explosion. For half a century, this remained nothing more than elegant mathematics scribbled on a chalkboard, a beautiful but unconfirmed prediction. We had never observed a black hole explode. We had never detected a Hawking burst, that is, until perhaps right now. The news rippling through the physics community this month is genuinely earth-shattering. Our observatories have registered a particle, a neutrino of extraordinarily high energy that completely breaks the established rules. It slammed into our detectors with such immense force that it's comparable to being struck by a bowling ball hurled from across the galaxy. It carried an energy level 100,000 times greater than anything our most powerful particle accelerators, like the Large Hadron Collider, can generate. When astronomers traced its path back to its point of origin, they were met with nothing. No supernova remnant, no active galactic nucleus, no gamma-ray burst. Just empty, quiet space in a region of the sky perfectly consistent with the standard model of cosmology. This particle should not exist. There is nothing in that part of the sky capable of delivering such a powerful punch. So, scientists began systematically eliminating potential suspects. Could it be a collapsing star? No. The energy signature was wrong. Could it be the merger of two neutron stars? No. We would have detected the accompanying gravitational waves. One by one, every single conventional explanation crumbled under scrutiny. We were left with a ghost, an impossible object. And that's precisely when the research team at the University of Massachusetts Amherst proposed their radical solution. They declared, "We are witnessing the death rattle of a monster, but not a monster born from the collapse of a star. A monster born from the Big Bang itself, a primordial black hole." Let's take a moment to truly visualize what a primordial black hole, or PBH, actually represents. These are not the black holes you see dramatized in films like Interstellar. Those are stellar mass black holes, formed when a massive star exhausts its nuclear fuel and its core collapses under its own immense weight. Those are substantial objects, comparable in size to a city or our Sun. Primordial black holes are fundamentally different. They didn't form from stars because they formed before any stars existed. They came into being within the very first second of the universe's existence. Back then, the cosmos was an incredibly hot, dense, and chaotic soup of pure energy. It was expanding at a phenomenal rate, but it wasn't perfectly uniform. There were clumps, tiny, minute fluctuations in density. Some regions were marginally denser than their surroundings. And because the ambient pressure and energy were so unimaginably intense, these dense patches could simply collapse directly into black holes. Just like that. Pop. A black hole is born. But because the early universe was such a chaotic place, these primordial black holes could be born with almost any mass. Some could be enormous. However, a vast multitude of them would be incredibly tiny, microscopic. Imagine the mass of a large asteroid, compressed into the volume of a single atom, or the mass of a mountain, squeezed down to the size of a proton. These minuscule, ancient black holes have been silently adrift throughout the universe for the entirety of its 13.8 billion year history. They are dark, they are silent. We cannot detect them with conventional telescopes because they are far too small to noticeably block background starlight, and they lack the glowing accretion disks of superheated gas that typically betray the presence of larger black holes. They are the ultimate stealth objects, invisible to our prying eyes. But remember Hawking's rule: small black holes evaporate much faster. If you run the precise calculations, a primordial black hole born with a very specific mass, roughly equivalent to a large pyramid, or perhaps a small cruise ship, would take exactly 13.8 billion years to completely evaporate. Do you see the profound coincidence? That is precisely the current age of the universe. This means that right now, at this very moment, scattered across the cosmos, there should be a whole generation of primordial black holes reaching their expiration date. They are hitting that final stability limit. They are going critical. So, if we happen to observe a random, unexplained burst of ultra-high energy particles emanating from an otherwise empty patch of space, it is practically the smoking gun we've been searching for. It is a primordial black hole sending out its final signal: my time is up. But this is where the narrative takes an even stranger turn. And this is precisely why the headlines are claiming it could explain almost everything. Because the particle they detected was simply too energetic. Even a standard textbook exploding black hole shouldn't have been capable of producing a particle with that much power. Standard Hawking radiation is a relatively smooth thermal process. It's a slow leak. It shouldn't produce a single distinct neutrino with such an incredibly focused, powerful punch. As revolutionary as Hawking's theory was, it alone proved insufficient to account for this observation. The physicists working on this problem were forced to incorporate a new ingredient into their equations. And this new ingredient is where we truly step into the uncharted territory of new physics. They call it dark charge. The theory, formerly known as the dark charge quasi-extremal primordial black hole hypothesis, goes something like this. What if these ancient black holes aren't composed purely of gravity? What if they also carry a charge? Not an electrical charge like a battery, but a charge originating from the dark sector. We know dark matter exists. We know it constitutes approximately 85% of all the matter in the universe, yet we have absolutely no idea what it actually is. We have never directly detected a dark matter particle. We only infer its existence from its gravitational effects holding galaxies together. However, many theoretical models suggest that dark matter has its own set of rules, its own forces, perhaps even its own form of electromagnetism, all completely hidden from our visible universe. The team at UMass Amherst proposes that these primordial black holes absorbed vast quantities of this dark charge during the violent energy of the Big Bang. Now consider what adding a charge does to a black hole. If you take two magnets with the same polarity, they repel each other. They push apart. Inside a black hole, if it accumulates too much of a similar charge, that repulsive force begins to counteract the inward pull of gravity. It fights to push the black hole apart from the inside. As the black hole slowly evaporates and shrinks, its gravitational pull weakens because its mass is decreasing. However, the dark charge it holds remains constant, becoming more and more concentrated as the volume decreases. Eventually, the outward pressure exerted by this concentrated dark charge balances the inward crush of gravity. The black hole enters a state known as quasi-extremal. It becomes in effect a loaded spring, pushed to the absolute theoretical limit of stability, teetering on the edge. It desperately wants to fly apart, but gravity is just barely managing to hold it together, and then it snaps. The evaporation is no longer a slow, gradual leak. It becomes a catastrophic, structural failure. The black hole violently sheds its outer layers in a desperate attempt to rid itself of that destabilizing dark charge. And because this process involves the dark sector, an entirely different realm of physics, the energy released is absolutely colossal. It pumps out particles with energies that are simply impossible to achieve within our normal, visible universe. That impossible neutrino we detected? That was the high-energy shrapnel, the smoking debris from a dark-charged black hole tearing itself apart at the seams. Why does this matter so much? Why do I claim it could explain everything? Let's break it down. Problem number one, dark matter. For decades, we've been on an exhaustive and so far fruitless hunt for hypothetical particles like WIMPs, weakly interacting massive particles, or axions to account for dark matter. We've built gigantic, exquisitely sensitive detectors deep underground in former mines and caverns to catch a whisper of their passage. We have found absolutely nothing. The scientific community is growing desperate for answers. But this discovery has the potential to completely flip the script. If primordial black holes are real, and if they carry this dark charge, then they themselves are the dark matter. We don't need to invent new, exotic particles floating around. We just need a universe filled with vast numbers of tiny, incredibly massive, charged black holes. The cosmos isn't permeated by some invisible, inert dust. It's filled with invisible, heavy, charged cosmic bullets. This single observation could potentially solve the biggest missing mass problem in all of cosmology. We may have finally found the ghost matter. It's just black holes. Problem number two, probing the Big Bang. We cannot directly observe the Big Bang itself. The early universe was an opaque, roiling plasma for the first 380,000 years of its existence. We cannot peer back beyond that point using light. Our view is blocked by a wall of fire. We are essentially blind to the actual moment of creation. But these primordial black holes, they are time capsules forged in that very first, inaccessible second. If they possess dark charge, it tells us definitively that the dark sector was not just present, but was active and energetic right from the very beginning. It provides us with a direct, empirical probe into the physics of the infant universe, a realm we thought was forever hidden. Analyzing the explosive death of a primordial black hole is like finally receiving and opening a letter written by the Big Bang itself, sealed for nearly 14 billion years, and delivered to us just now. Problem number three, the information paradox and quantum gravity. This is the big one, the holy grail of theoretical physics. For a long time, physicists have been deeply troubled by the idea that if a black hole evaporates completely into Hawking radiation, all information about everything that ever fell into it is simply deleted. This fundamentally breaks one of the most cherished laws of quantum mechanics, which states unequivocally that information is never truly lost. This is the core of the famous black hole information paradox. But if the black hole explodes at the end of its life, if it has this violent, structured final event, it opens the door to the possibility that the information is not lost, but released. It bounces back. This aligns incredibly well with theories like loop quantum gravity. In loop quantum gravity, space-time itself is not a smooth continuum, but is composed of tiny, discrete, indivisible grains. You cannot compress matter and energy infinitely. Eventually, you hit this fundamental granularity. The collapse must stop. The black hole cannot shrink all the way down to an infinitely dense point of zero volume, a singularity. It has to bounce. It would create what's known as a Planck star, or potentially transition into a white hole. The detection of this specific type of explosion strongly suggests that the singularity, that problematic point of infinite density, does not actually exist. There is no ultimate destruction. There is a transition, a bounce, a quantum event. The explosion we may have witnessed is the very moment when gravity reverses, turning itself inside out. It suggests that general relativity, the physics of the very large gravity, and quantum mechanics, the physics of the very small, finally meet and shake hands at the moment of a black hole's death. We are seeing the long-sought unification of physics playing out live in the sky. This is why physicists are using loaded terms like smoking gun. This isn't just a weird one-off particle event. It is a single key that seems to fit perfectly into 3 or 4 different fundamental locks simultaneously. It fits the dark matter lock. It fits the Big Bang lock. It fits the quantum gravity lock. The convergence is almost too perfect to be a random coincidence. Let's take a step back and consider the picture of the universe this paints for us. We used to think of the night sky as a relatively static, quiet place, punctuated only occasionally by a dying star or a distant galaxy. But this new view is far more dynamic, far more violent. It implies that the seemingly empty space between the stars is actually teeming with these tiny, ancient monsters, trillions upon trillions of them. Most are dormant, completely invisible, just points of immense mass scattered throughout the darkness. But every so often, one of them runs out of time. One of them screams. Imagine sitting in a completely dark room. You believe it's empty, devoid of anything. But then you hear a sudden pop, see a brief flash of light. You suddenly realize the room is actually full of firecrackers with extremely long fuses, and all the fuses are of different lengths. We are just now beginning to wake up to the fireworks display that has been going on around us since the beginning of time. This discovery also fundamentally alters our future prospects. If we can reliably detect and study these explosions, we can begin to map the distribution of these primordial black holes. We can chart the skeleton of the universe's mass, understanding how galaxies truly formed, seeded by these heavy, invisible anchors. And perhaps most excitingly, it opens up the possibility of studying the most extreme high-energy physics without having to build ever larger colliders. We don't need to construct a particle accelerator the size of our solar system to test the limits of physical law. The universe is doing it for us, for free. These exploding black holes are nature's own perfect particle accelerators. They are cosmic laboratories, available for our observation. All we have to do is watch and listen. The skeptics, of course, are still out in force, and rightfully so. Science is, by nature, conservative. They will argue that perhaps it was just an extraordinarily weird magnetic field interaction around a neutron star. Maybe we misinterpreted some glitch in the detector data. And that is a good thing. That healthy skepticism is crucial for the scientific process. We absolutely need to verify this. We need to see another event and then another. If this is real, it shouldn't be a one-off anomaly. We should observe a whole spectrum of these explosions with varying energies and characteristics. But the statistical confidence surrounding this particular result is remarkably high. The dark charge model fits the observational data with what scientists call 5 sigma precision. That is the gold standard for a discovery in physics. It means there is approximately a 1 in 3.5 million chance that this result is a mere statistical fluke. In essence, it's almost certainly not a fluke. The data is screaming at us, loud and clear, that something genuinely new and unprecedented is happening. We are standing at a threshold. In the early 20th century, we made the monumental discovery that atoms actually exist. Then we discovered they could be split. Then we discovered that the stars are powered by that very splitting. Now in the 21st century, we are discovering that space-time itself has distinct, discrete packages, black holes that behave almost like particles. They decay, they explode, they carry charge. The fundamental line between matter and gravity is beginning to blur. We just saw a black hole explode. Let that monumental statement truly sink in. We have witnessed the death of an object that was, by all classical accounts, supposed to be immortal. And in its final, dying moments, it illuminated the hidden, dark side of the universe for us to see. So the answer to the question, did we just see a black hole explode, is almost certainly a resounding yes. And the answer to the question, does it explain everything, is surprisingly close to being a yes as well. It gives us the missing matter. It gives us a window into the beginning of time. It gives us a potential pathway to the unification of forces. It is the piece of the cosmic puzzle we have been blindly searching for 100 years, the one that was hiding under the cosmic sofa all along. The universe is strange. It is chaotic. It is filled with dark monsters carrying dark charges from a dark era. And isn't that simply magnificent? It means there is still so much left to explore, so many profound mysteries waiting to be unraveled. We haven't solved it all yet. In fact, we are just getting started on this new, exciting leg of the journey. Thank you, from the bottom of my heart, for watching. This is a deeply complex topic, and its implications are truly immense. I want to know what you think. Does the idea that dark matter is simply made of ancient black holes resonate with you, or do you still lean towards the possibility of exotic unknown particles waiting to be discovered? Let me know in the comments section down below. I genuinely read every single one. If you enjoyed this journey to the very edge of known physics, please consider obliterating that like button just like a primordial black hole obliterates its own event horizon. And if you haven't already, please subscribe to the channel. We have so many more cosmic mysteries to cover, and you won't want to miss what comes next. Until then, keep looking up. The darkness is full of surprises. Let's go even deeper for a moment. To truly appreciate the magnitude of this explosion, we have to fully appreciate the nature of the prison wall itself, the event horizon. Imagine a powerful waterfall, a massive river flowing swiftly towards a sheer cliff. The water accelerates as it approaches the edge. Now picture a determined fish trying to swim upstream against the current. If the fish can swim faster than the river's flow, it can escape. But right at the precipice of the cliff, the water is falling faster than the speed of sound. Even if that fish could swim at the speed of sound, it would be carried over and fall. The event horizon of a black hole is the point in spacetime where space itself is falling inward towards the singularity faster than the speed of light. Light itself is that fish. It swims upstream at its maximum cosmic speed of 300,000 kilometers per second, but the fabric of space is dragging it downwards even faster. For decades, we believed this boundary was a perfect, unbreakable seal. We were convinced that any information crossing that point was lost to our universe forever. This is the essence of the information paradox. If I were to toss a book containing all of human knowledge into a black hole, according to classical theory, that book is irrevocably gone. The information it contains, the words, the ideas, the structure, is permanently erased from the cosmos. But quantum mechanics, our most successful and accurate theory of reality, insists that information is fundamentally indestructible. You can take a physical book and burn it to ashes, but in principle, if you could collect every single ash particle, every molecule of smoke, and every last photon of heat and light released, you could theoretically reconstruct the book's information. Standard black hole theory seemed to break this fundamental law because it said the book's information was truly permanently deleted. But this new explosion scenario offers a potential fix. If the black hole eventually explodes, it returns all the energy, and crucially, the information encoded in that energy, of the book back to the universe. It might be scrambled beyond recognition, thoroughly chewed up and transformed into a burst of high-energy neutrinos and gamma rays, but it comes back. It is not lost. The universe, it seems, creates backups. Nothing of information is ever truly lost. I mentioned the dark sector earlier, and I want to double-click on that concept because it often sounds like pure science fiction. It's not. It's the cutting edge of modern cosmology. We know from precise measurements that normal visible matter, the protons, neutrons, and electrons that make up you, me, the stars, the planets, and every speck of dust, accounts for a paltry 5% of the total mass energy budget of the universe. Just 5%. That's it. The remaining 95% is the dark sector. Approximately 27% is dark matter, and a whopping 68% is dark energy. We are the anomaly. We are the rare, weird foam on the surface of a vast, dark, and unknown ocean. The term dark sector is simply a generic placeholder for whatever creates and governs that 95% of reality that we cannot directly see. For a long time, we hoped the dark sector was simple. Perhaps just one type of boring, inert particle floating around, interacting only through gravity. But why should it be simple? B. The normal sector, our stuff, is incredibly complex. It has electromagnetism, the weak nuclear force, the strong nuclear force, quarks, leptons, neutrinos. We have chemistry, we have biology. Why would the dark sector, which constitutes the overwhelming majority of existence, be any less complex? Maybe there is dark electromagnetism, allowing for dark atoms and molecules. Maybe there is dark chemistry. Perhaps there are even dark stars, shining with an invisible light. The theory of dark charge on these primordial black holes strongly suggests exactly that. It suggests the dark sector possesses its own forces. It has its own form of complexity. These ancient black holes interacted with that hidden complexity in the infant universe. They absorbed and stored that dark charge, and now, billions of years later, they are violently spitting it back out into our observable reality. We are receiving a message from the shadow universe. It tells us that the invisible world is just as rich, just as complicated, and just as dynamic as the visible one we inhabit. I want to circle back to loop quantum gravity, or LQG, because it's a key piece of this puzzle. This is one of the main theoretical competitors to string theory. String theory attempts to unify physics by describing all fundamental particles as vibrating strings, often requiring 10 or 11 spatial dimensions. It's mathematically elegant, but notoriously difficult to test experimentally. Loop quantum gravity takes a different, grittier approach. It posits that space itself is not a smooth, continuous fabric. Instead, it's made of tiny, discrete loops of the gravitational field. Think of a fabric t-shirt. From a distance, it looks smooth, but if you look closely under a microscope, you see the individual threads woven together. According to LQG, if you could look at space at the most fundamental level, the incredibly tiny Planck scale, you would see a similar structure, a weave of discrete loops. Because space is made of these fundamental, indivisible chunks, you cannot crush something down to an infinitely small point of zero size. There is a minimum possible volume, a smallest unit of space. When a black hole's core collapses, it squeezes matter and energy down until it hits this fundamental graininess of space-time, and then it can physically squeeze no further. The collapse halts, immense pressure builds up, and eventually, like a compressed spring, it rebounds. This is the hypothesized quantum bounce. The black hole, in a sense, turns itself inside out and transitions into what is known as a white hole. A white hole is the exact opposite of a black hole. A black hole permits nothing to escape its grip. A white hole permits nothing to enter. It can only spew matter and energy outwards. While the dark charge model is currently the leading explanation for this specific ultra-high-energy neutrino, many theorists believe the observed explosion is essentially the observational signature of this transition to a brief white hole phase, a brief, incredibly bright flash where the black hole violently ejects its compressed core. If this is true, our universe could be filled with these Planck stars, tiny, incredibly dense white holes that are the stable remnants of dead or transformed black holes. And what would a Planck star look like to our telescopes? It would possess mass. It would exert gravity. But it would emit no light unless it was in the process of actively exploding. In other words, they would look exactly like dark matter. Do you see how it all connects? Loop quantum gravity, white holes, dark matter, and these cosmic explosions. It is beginning to form a remarkably consistent, unified picture of a fundamentally quantum universe. So, where do we go from here? We wait for the next one, and the one after that. The detection of a second, similar event would dramatically confirm the pattern. If we observe a third, we can begin to do real statistics. We can start measuring the mass spectrum of primordial black holes. We are, in effect, commencing the first census of the invisible population of our galaxy. This is day one of a new science, black hole archaeology. We are digging up the fossils of the Big Bang, but these particular fossils are still very much alive, and they are detonating with the power of countless atomic bombs. The universe is not silent. It is snapping, crackling, and popping with the residual energy of ancient physics, playing out on the grandest scale. And we, for the first time, are finally listening. Did we just see a black hole explode? Yes, and it changes everything. Thanks for watching. If you want to dive even deeper into the mathematics and the specific details of this research, I've linked the original scientific paper in the description below. And if you have your own theories about what else these primordial black holes could be doing, perhaps seeding life across the cosmos or acting as hidden portals to other dimensions, please tell me in the comments. Stay curious, stay fascinated by the universe around you, and I'll see you in the next video.